Greetings to all and welcome to this lecture. We are in module 12, small signal modeling, lecture number 3, a medium frequency small signal model part 2. In this lecture, we will discuss about how to extract the small signal capacitances as what we have defined in previous lecture: CGS, CGD, CBS, CBD and CGB under strong inversion operation. We will also see how the behavior of these capacitance vary in saturation and non-saturation region. These are the learning outcomes of this lecture, which helps you to define the intrinsic capacitance expression of the MOSFET in strong inversion. This will help you to define the relationship between gate, body and channel capacitances using the channel charge distribution, meaning when you change the terminal voltages, the gate charge, which is QG dash or QG, and the bulk charge changes. Accordingly, we will define the capacitances in strong inversion. We will also see how these capacitances are interrelated in strong region of operation. Let us do a quick recap. In previous lecture, we said that when the terminal voltage vary with the medium frequency with a small magnitude, then there will be a charge storage effect. Because of charge storage effect, we can simply reflect the change in the charge with respect to change in the terminal voltage as capacitance, right? We said that this is very important when you are actually deriving the small signal model for a MOSFET. In addition to the previously defined conductance and transconductance parameter, we do have some charge storage element because the terminal voltage frequency is not very low. So, we define in total 5 capacitances as CGS, CGD, CBS, CBD and CGB, and we have incorporated these 5 capacitances in our small signal model. Later, we said that there should be a validity of this model, meaning when the frequency of the input signal is very high, then this model is not applicable. So, we have to define an upper limit of the frequency with which this model is applicable. We said that upper limit can be defined as mu into VGS minus VT divided by alpha into L square. So, the model validity strongly depends upon the dimension of the device, the operating region of the device, in which terminal my signal is changing, either source, body, drain or gate, right. So, the model validity depends on various factors. Now, let us see how we can extract these capacitances, these small signal capacitances in strong region of operation. So, we will follow the same procedure. To calculate the capacitance, we will calculate the change in the gate charge or change in bulk charge with respect to change in terminal voltage. So, this value will give me what? CGS. So, let us consider the gate charge expression, which is given by this. In previous lecture, when we were discussing about large signal quasi-static analysis, we derived the charge equation for gate charge, bulk charge, inversion charge, etc. So, we have taken this equation from that lecture and we are going to derive or we are going to differentiate this equation with respect to terminal voltage. Before proceeding, let us consider few assumptions. The first assumption for simplicity is that alpha 1, right, for source reference model considered to be constant, meaning when we are going to differentiate this alpha, we will consider it as constant, and alpha 1, which is nothing but 1 plus gamma divided by 2 times of square root of phi naught plus VSB, right. This is also can be replaced as n, right, and this is can be replaced as 1 plus dVt divided by dVSB. We have derived that fact as Vt is equals to Vt naught plus gamma times of phi naught plus VSB minus square root of phi naught. So when you take differentiation with respect to VSB, you will get gamma divided by 2 times of square root of phi naught plus VSB. So with this assumption, we will move forward to calculate CGS. So let me rewrite the equation as QG is equals to W into L into COX dash into VGS minus VT divided by alpha into alpha minus 1 plus 2 by 3 into 1 plus eta square divided by 1 plus eta plus gamma times square root of phi naught plus VSB minus Q naught. Here we are considering there is no oxide charge, or the oxide charge will be fixed. So the differentiation of Q naught will be 0. Similarly, this is represented as total capacitance because we are multiplying with the area. So total capacitance COX into VGS minus VT divided by alpha into alpha minus 1 plus 2 by 3 1 plus eta square by 1 plus eta. Again, we are not considering this effect, right, because this factor is related with alpha. We can derive that gamma divided by square root of phi naught plus VSB is in terms of alpha, which we have considered constant, and hence the differentiation will goes to 0. So this is the general expression of QG. And now I am interested in what is delta QG divided by delta VS with a negative sign. This will give me CGS, right? So we can use a chain rule, delta QG divided by delta VGS into delta VGS divided by delta VS plus delta QG divided by delta eta into delta eta divided by delta VS. Let me call at equation number 1. We will calculate the different quantities and put in equation number 1 to find out the overall CGS. So what is QG divided by delta VGS? This is nothing but you differentiate this equation, delta QG divided by delta VGS will give you COX into alpha minus 1 plus 2 by 3 into 1 plus eta square divided by 1 plus eta, and as you are doing differentiation with respect to VGS, you will get what? Alpha. So let us consider this is in equation number A. Now delta VGS with respect to VS is what? VG minus VS. If you differentiate with respect to VGS, or sorry VS, you will get what? Minus 1. Equation number B. Now we need to differentiate this equation with respect to eta. So delta QG divided by delta eta will give you what? COX into VGS minus VT divided by alpha into 2 by 3 and differentiation of this factor, which is nothing but 1 plus eta whole square, 1 plus eta into 1 plus 2 eta minus 1 plus eta square. When you are going to solve this, you will get COX into VGS minus VT by alpha into 2 by 3, denominator 1 plus eta whole square. In numerator you will get 1 plus 3 eta plus 2 eta square minus 1 minus eta square. So this 1 and 1 get cancelled. 3 eta minus eta 2 eta, and 2 eta square minus eta square is VGS minus VT divided by alpha into 2 by 3 into 2 eta plus eta square divided by 1 plus eta whole square. This is what delta QG divided by delta eta. Let us recall this as equation number C. Now we need to find delta eta by delta Vs. So eta is defined as 1 minus Vds divided by Vgs minus Vt into alpha. So you need to differentiate with respect to Vs. So delta eta by delta Vs is equals to minus Vgs minus Vt whole square into Vgs minus Vt into this, the differentiation with respect to S. So it will give you what? Alpha into minus 1, right? Because Vds is nothing but Vd minus Vs, and when you are going to differentiate with respect to Vs, you will get minus 1 minus alpha into Vds. Again, if you are going to differentiate this with respect to Vs, you will get what? Minus 1. Take minus 1 out, and Vgs minus Vt into alpha also out. So alpha into Vgs minus Vt is taken out. You will left with 1 minus Vds divided by Vgs minus Vt divided by Vgs minus Vt whole square. So this get cancelled, and if you consider alpha is equals to 1, then delta eta by delta Vs can be written as 1 minus, this factor is what? 1 minus eta divided by Vgs minus Vt, right? You put back all these equation A, B, C, D to calculate CGS, then you will ended up with this equation. So the CGS equation is nothing but COX into 2 by 3 into 1 plus 2 eta divided by 1 plus eta whole square, right? This is the equation for gate to source capacitance. In a similar way, you can find what is the expression for CGD. So if you are going to calculate CGD, this is nothing but delta Qg divided by delta Vd with a negative sign. Now again you can simply use Qg equation, what we have used here, and instead of differentiating with respect to source, you can simply rewrite as delta Qg by delta Vd as delta Qg divided by delta eta into delta eta by delta Vd, right? We have this expression in equation number C. So you use this expression for equation number C and differentiate eta with respect to Vd. So eta is equals to what? 1 minus Vds divided by Vgs minus Vt into alpha. So when you differentiate delta eta by delta Vd is equals to, you will get minus alpha divided by Vgs minus Vt. Because you are differentiating with respect to Vd, then you will get only 1, right? You put back here, because of this negative sign, there will be a negative sign here, and this Vgs minus Vt and this alpha will get cancelled. Ultimately you will get COX into 2 by 3 into eta square plus 2 eta divided by 1 plus eta whole square. This is this factor. So likewise we calculated both the capacitances as CGS and CGD under strong inversion region of operation, where COX is nothing but the total intrinsic capacitance, right? Now let's see how we can calculate the body related capacitance. For that, consider this MOSFET. This is N plus, this is N plus, this is oxide, and you have gate this side, and you have a body this side. Now if you see, when you apply the constant voltage at the gate terminal and the body terminal, there will be a bulk charge, and also there will be a inversion charge. So this body capacitance is nothing but a capacitance which is formed between a field induced N region, right, and P region. So it is nothing but NP junction, right? This is inversion charge, which is nothing but N, which is field induced N, and here it is P type body. So there will be a reverse bias junction because you are changing what? the body voltage. So because of that, there will be a reverse bias PN junction, which is nothing but CBC dash, as can be given as delta Q divided by delta V, where we know QB can be given as 2 into Q into Na into epsilon S into square root of psi s, right? And when you differentiate it, you will get this. So ultimately CBC dash is nothing but the capacitance present between gate and body and looking from the body side. It is similar as the Cox, right? So when you look from the gate side, Cox is the capacitance present between that, and when you look from the body side, it will be CBC, right? Now as CBC is dependent on VCB, so you cannot simply say it is a oxide capacitance which is similar as Cox, because to calculate the overall capacitance Cox, we simply multiplied with the area, W into L into Cox dash. However, here this CBC dash is dependent on VCB, so you cannot simply multiply with the area. So you need to what? Integrate between 0 to L to find out the overall CBC. So the capacitor due to this depletion region is CBC, right? And following a simple way, we are simply multiplying CBC into area, where CBC is calculated at a particular VCB, right? If let's say the VCB voltage, the voltage between VSB and VDB is the limit of VCB, right? VCB varies from VSB at the source side to VDB at the drain side. Now if we fix a VCB voltage at a particular channel region, let's say at a location X, then accordingly we can calculate CBC and multiply with the area. So how we can calculate a particular value of VCB? We have done this analysis when we were saying that, consider this is my source end, consider this is my source and this is my drain, and if I am interested to calculate a potential at location X, then I can use simply as this is Vx, right? So my limit of VCB varies from VSB at the source side to VDB at the drain side. VDB can be written as VDS plus VSB. Now VDS is the voltage exactly at the drain side. If I am interested in at a location X, then what I can write? I can write that VCB varies from VSB at the source end and Vx plus VSB at location X in the channel. Now how can I calculate Vx? By using function of eta. Eta is equals to 1 minus VDS divided by VDS dash. So if I want to calculate at a location X, I can simply rewrite as 1 minus Vx divided by VDS dash. So Vx can be written as 1 minus eta into VDS dash. That is what we have written, a equation for VCB which varies from VSB to Vx, and Vx is nothing but 1 minus eta into VDS dash with some correction factor. This is an empirical parameter, lies between 0.1 to 0.2. So now to conclude this, the CBC is the body capacitance which varies along the channel. However, to simplify the model, we find out a particular value of VCB which is in terms of Vx, and at that point we calculate CBC dash and simply multiply the area. So this will give me CBC which is in parallel or which is similar as Cox when you are talking about gate side, and when you are talking about body side it is CBC. So to calculate the other capacitances like CBS and CBD, I can use the simple approximation. I can use the same approximation what we have done so far to calculate CGS and CGD. Remember, in CGS we have COX into 2 by 3 into 1 plus 2 eta divided by 1 plus eta whole square. So as we are looking from body side, this COX is replaced by what? CBC, 2 by 3, and that factor will be same, 1 plus 2 eta divided by 1 plus eta whole square. Similarly, CGD can be written as CBC into 2 into eta square plus 2 eta divided by 3 into 1 plus eta whole square. Here this is what? This is COX and this is CBC, 2 by 3 into eta square plus 2 eta divided by 1 plus eta whole square. Now which is larger? Obviously COX, because the oxide thickness is smaller and hence CBC is smaller. If the oxide thickness is smaller, COX will be larger and CBC will be smaller. So though CGS and CBS follows the same trend, but the value of CBS will be smaller. We will see in our coming slides what is the trend of CGS and CBS. To move further, we can divide these two capacitances and find the relation between CBS is equals to CBC divided by COX into CGS, right? This factor is defined as BC. So CBS can be written as BC into CGS and CBD can be defined as BC into CGD. Now what is BC? If you see, CBC we have defined in previous slide, right, divided by COX. So ultimately it will be 2 into Q into Na into epsilon S divided by 2 times of COX into square root of phi naught plus VSB. What is this parameter? Square root of 2 into Q into Na epsilon divided by COX is a body factor. So ultimately this can be replaced by gamma divided by 2 into square root of phi naught plus VSB, right? So I can simply write BC is nothing but gamma divided by 2 into square root of phi naught plus VSB. This is similar as BG, what we defined in our previous lecture. BG was defined as GMB divided by GM is equals to BG, where we said that for BG can be defined as gamma divided by 2 into square root of phi naught plus VSB plus some constant into 1 minus eta into VDS dash, and for small value of VGS and VDS, this is nothing but gamma divided by 2 into square root of phi naught plus VSB. This is also nothing but alpha 1 minus 1 or n minus 1 or dVT divided by dVSB. We have done all these calculations in previous lectures. So we can simply relate the ratio of GMB by GM and CBS divided by CGS are same. So CBS by CGS is equals to CBD divided by CGD is equals to CBC by COX is equals to GM by GM or GMB by GM, which is almost same under the approximation that VGS is very small and VDS dash in turn will be very small. Now we have another capacitance we can calculate as gate to body capacitance, meaning you have a gate like this and a body like this. If you change a small voltage in the body, then what will happen? The depletion region changes, right? The change in the depletion region charge is actually reflect the change in gate charge. So delta Qg divided by delta Vp can be defined as gate to body capacitance, which in turn simply visible as CBC, which is this charge or this capacitance, and COX, are in series. So if I say this is COX, this is CBC, right, then these two capacitances are in series. That is what we are getting some expression like this in our CGB equation. So if you measure the overall capacitance between gate and body, then the two capacitances are coming in series, right? So how we can calculate this? By using an expression, the charge neutrality, meaning QG plus QB plus QS plus QD is equals to 0, right? The charge balance equation, out of which this can be written as QG is equals to minus QB minus QS minus QD. If I want to find out the difference or the change in the QG with respect to change in the body voltage, I can rewrite as minus delta QB divided by delta VB minus delta QS divided by delta VB minus delta QD divided by delta VB. This can be simply modeled as minus CBC minus CBS plus CBD, right, CBD. With this you can also calculate, or physically it is also evident that both the capacitors are coming in series. However, we do have another factor which is called shielding factor, meaning when you apply the voltage, then the inversion charge is coming between gate and body like this. So now if you are in strong inversion, then what will happen? The inversion charge acting as a shielding layer, and hence this capacitance is shielded by some amount. We will see how this amount can be calculated under non-saturation and saturation region of operation. So it is clear that both the capacitance are not exactly in series, meaning you cannot simply use COX into CBC divided by COX plus CBC. You have to have some shielding parameter which is coming out with this. So if you do this detailed explanation, you will get this shielding factor. Now let us see how these capacitances, the 5 capacitances, vary in different region of operation, that is non-saturation and saturation. So we are plotting the capacitances with respect to VDS, right? So let's calculate the values of these capacitances for two different points. The first point is we are considering at VDS is equals to 0. If VDS is equals to 0, eta will be equals to 1, because eta is given as 1 minus VDS divided by VDS dash. So if VDS is equals to 0, eta will be 1. Now you go back and calculate CGS, CGD, CBS, CBD by putting eta is equals to 1. So let us consider if I put eta is equals to 1 here, this will give me what? 2 by 3 into 1 plus 1, or sorry 1 plus 2 divided by 1 plus 1 whole square into COX, which is nothing but 2 into 3 divided by 3 into 4. So this 3 and 3 get cancelled, you will left with half of COX, right? That is what we are getting here. CGS and CGD are half of COX. Similarly, CBS and CBD are half of CBC, and CGB is equals to 0. So we just mark these points here at VDS is equals to 0. So VDS is equals to 0. So this is the point which shows CGS and CGD. This is the point which marks as CBS and CBD, and this is the point which shows CGB is equals to 0. Now why it is so? To understand physically, let us consider a fictitious transistor again, and we are considering that VDS is equals to 0. If VDS is equals to 0 means what? The drain voltage and the source voltage at same potential, right? Now what happens is, suppose if you are increasing a small voltage at the source side, then the drain voltage is also increases by the same amount, meaning the increase in the source voltage by some small amount increases the surface potential here. Because of the surface potential, there is a change in bulk charge. That bulk charge is reflected into the change in gate charge, which give rise to a capacitance. As we are linearly changing the source and drain voltage, so we can simply say the overall capacitance measured between these terminal, which is nothing but what? COX, right? That is an overall capacitance, is just split into half, right? Half will go at the drain side or half will go at the source side, meaning the linear change in the body or the gate charge is captured by the drain and the source at VDS is equals to 0, right? That is what we are getting half term. The similar theory is applicable when we are talking about the bulk charge or CBC. But remember, the depletion region thickness is wider. Because of that, CBC is smaller than what? COX. So we are getting the same distribution when the VDS is equals to 0. But now what happens when VDS is equals to 0 and you are in strong inversion? It means you have applied the gate voltage such a way that this region is completely filled with inversion charges. There is no current, but yes, the device is having full amount of inversion charges. You can see that you have a gate plate and you have an oxide below which there is an inversion charge. So that inversion charge is completely shielded the gate electric field, and hence the effective capacitance measured between gate and body will be what? CGB is 0. That is what the physical sense to get CGB is equals to 0, right? So we mark these 5 points here. Now we will calculate these values for the second case, considering VDS is equals to VDS dash, meaning you are entering from non-saturation region to saturation region. In this condition, what is eta? Eta is equals to 0. So when you put back eta is equals to 0 in your previous equations, you will get CGS is equals to 2 by 3 into COX, CGD equals to 0, important point to note. Similarly, CBD is equals to 0, CBS is 2 by 3 factors of CBS, and CGB is not 0 now. Again, this is an important point. So physically, how can we understand that? As you increase the drain voltage. Now if you increase the drain voltage, you are entering from non-saturation to saturation region, means the channel will get tapered, right? There will be a pinch off region here. If there will be a pinch off region, the change in the charge is not captured by the drain side, and hence you can simply think whatever be the change in the gate charge happens here, it is happened near the drain, near the source, and but not near the drain. So there is no change in gate charge with respect to drain voltage when you are in saturation. Because of that, CGD is equals to 0. The same theory is applicable when you are talking about CBD. Now why CGS is 2 by 3 of COX? Why not complete COX? Because in our previous theory we said that the inversion layer is like a metal, is like a thickness, right, of the charges. If we consider the metal thickness, then no question of 2 by 3. But this is not the case. When you are increasing Vs, what will happen? The surface potential will increase near the source. Ultimately, the surface potential is no longer be completely uniform throughout the channel, because at the drain side you are in pinch off condition. So the surface potential is increases here, and ultimately what happens? It is varying along the channel. Because of that, the distribution of the charge carrier is no longer complete COX, it is with some less than COX, and mathematically proven as 2 by 3 factor will come into picture. The same thing will happen here in CBS, we will get 2 by 3 factor. Now why CGB is not 0? Because there is a pinch off, right? So there is a region with which the electric line of gate to body is get seen some capacitance, and hence we do have 1 by 3 factor of COX into CBC saturation into COX plus CBC sat. Now we are in position to plot these values of capacitances along VDS. So we are plotting the capacitance along VDS. Considering this is a non-saturation region, it means my VDS is less than VDS dash, and here VDS is greater than VDS dash. This is the point where eta is equals to 1. This is the point where eta is equals to 0. You see, when you are moving from non-saturation to saturation, your CGS is increases from half of Cox to 2 by 3 of Cox, whereas CGD goes from half of Cox to 0, and this transition from non-saturation to saturation will be smooth, right? Similarly, CBS and CBD can be defined in a similar sense. However, the value of these capacitance will be lesser. We have already argued that the value of CBC is lesser than COX because the depletion region thickness will be higher, and CGB as plotted as it is 0 earlier, but now in saturation region because of pinch off there is significant amount of CGB exists. So these are the values which we plotted with respect to VDS, and we have seen that how the small signal capacitances do a transition between saturation and non-saturation region of operation. So let me summarize this lecture as we have discussed or extracted the intrinsic capacitances in strong inversion. We basically talked about CGS, CBS, CGD, CBD and CGB. We said that the extraction of these capacitances are very important and they are strongly dependent on the region of operation, as if you are extracting these capacitances for VDS is equals to 0, then roughly the value of CGS and CGD are same as half of Cox, and similarly this value is half of CBC, whereas CGB is equals to 0. And when you are extracting these capacitance for saturation region, we will get CGS is equals to 2 by 3 of Cox and CBS as 2 by 3 of CBC. On the other hand, CGD is equals to 0 and CBD is equals to 0. So we will stop here for today. Until then, take care.